Hello, physics students. This is the problem we're going to tackle today is a little bit challenging. It has to do with circular orbits and the periods of those. And so here it is, problem 15 on Kappa Unit 7. So problem 15, Unit 7. Okay, circular orbits. We have a formula for the period. Okay, T stands for the period of the orbit. And the formula is 2 pi times the square root of r cubed over g times m. What the heck are these variables? R is the radius of the orbit of the circular orbit. G is a gravitational constant, and that gravitational constant is 6.673 times 10 to the negative 11th. Units are newtons times meters squared over kilograms squared. Now, in this is kind of that fudge factor that made the equation work, and so it's interesting. You come up with these constants of these in this universe that just apply to all these situations. Pretty impressive. But this you'd say, oh, I need to input this right away. Well, let's not jump ahead of ourselves, because we're going to see in the end that actually will cancel out. So it doesn't matter if you do or do not put it in, and so we'll just leave it alone for now. The M stands for the mass of the two bodies. The mass of the sun, in this case, sun plus, or star, whatever you want to call it. We don't know where this is at for the star, and the mass of the planet. Now, in this case, the mass of the star is so much bigger than the planet, we're going to assume that the mass of the planet does not matter, the mass of these two planets. So we're going to assume that, and you can do that, because if the star is way more massive than the planet, then it won't affect this much. And you have to have that assumption for this problem. So we're going to then use this formula. Okay, so we want to know it turns so many degrees. This little planet turns so many degrees. Well, if we knew the ratio of the orbits, so the ratio of the periods of the orbit, it would be useful to this equation. And so if we knew the orbital period of, say, which way did I do it? It really doesn't matter, but I did orbital period of planet X over the orbital period of planet Y. Okay? And we're going to fill in here. So it's 2 pi square root of r of x cubed. Square root is all over this, and g times m all over 2 pi. All right, now this would normally be r of y, but r of y is equal to r of y is equal to r of x. Okay, so what we're going to do here then is replace. So actually we'll just call it r of y for right now, and g times m. Okay, well, look what we can cancel out. We can cancel that out. Now this is under the radical, so you would have to call this, you can do this with radicals. Rx cubed over radical g times m all over radical equal sign between the two. Ry cubed over radical g times m. That's a property of radicals. So now we can cross these out, and we're left with this equation here, that the period of x over the period of y is equal to rx cubed, radical rx cubed over radical ry cubed. Excuse me. All right, so where do we go from here? Well, this equation, I didn't tell you, how did I get this equation? It's 2 to 1, meaning the radius is 2 times, x is 2 times that of y, as you can see that up here, that x's radius is 2 times that of y's. It's told you the ratio there is 2 to 1. So that's how that equation comes about. So now we're going to substitute in here. Let's maybe go to a different color. So the period of x over the period of y equals radical r. So we're going to, let's substitute in. I'm trying to see which way I did it. It didn't matter which way you did it, but I substituted in for y. Okay. And so I substituted in for rx and I got ry 2ry. So I basically replaced, in this equation here, I substituted this in for that. So it's the square root of this e cubed, sorry. Did I make sure I got that in there? Okay, good. Over radical ry cubed. Okay, with some more fancy algebra, we can do this. Another property of radicals is that we can split these like this. And this is, oops, cubed. Sorry, I forgot that in there. And this is ry cubed. Well, what can we do? These two cancel. So this is actually equal to 2 cubed, the square root of 2 cubed over 1. That's 1, because that's a 1. Okay, so what is 2 cubed and the square root, oops, what a calculator, 2 cubed and the square root of that, okay. So this is equal to 2.828, okay, and that's equal to this. All right, well, look what we have here. We're also told up in the problem that 98 degrees. That's the question. How many revolutions does this big one take when the little one takes a 98 degree? When planet X is rotated through 5 years later, planet X is rotated through 98 degrees. So if planet X is rotated through 98 degrees. Okay, so from here it's almost like dead overhead. It's about 90 degrees, 98 degrees, so it's a little past. So how many times did Y revolve in that time frame? So, but what's the ratio? So the ratio is of this equals, all right, well, X went 98 degrees. Well, 98 degrees is what fraction of a revolution? So we divide this, and 98 divided by 360 is 0.272 revolutions. So if this went this far, how much did the other do? Well, you simply take this, and for every one revolution, the orbital periods is this. This is how long it takes to do one revolution, and this is how long it takes to do one revolution. Okay, so if we just simply take this number here, this planet X went 0.272 revolutions, okay, and if we multiply the fact that it did 2.828 is the time it takes, we will get the fact that this planet Y did 0.7698 revolutions. And that is our answer. So the orbital periods, the time it takes to do one revolution, you can just set that up, and you know that if it does this, then you can multiply. If planet X did 0.272 revolutions, well, this one's Y is gonna do 2.8 times that amount. It's that much faster. Okay, it's going to be revolving at that much more greater of a rate. And so that's your answer. That's how many revolutions it would, and no units on the answer. That's a bit confusing, I understand. So give it a try, and maybe I'll redo the video and if needed.